And we're going to pick off with what we left off with. What's this here? Okay, no problem, Jules. Let me share first before I go to the document. I do that a lot. Okay. So last thing I had you do was the P series. And hopefully you guys got to this one here, E, and realized that all you needed to do was write it as a sum. And so that was just the sum starting at 1, running to infinity of 1 over n times square root of n, or n to the 3 halves. So P was 3 halves, greater than 1, and therefore it converges. So that one was kind of an interesting one. It gave you the terms, and you had to turn it into a sum. The next test that we need to learn is the integral test. And this is fairly straightforward as well in terms of when does it converge and when does it diverge. So we're going to be convergent. It says if the integral is convergent. So the question is, what does that really mean? Well, an integral is convergent if it gives back some number. And an integral is divergent if, for instance, it gives something like plus or minus infinity, or does not exist. And so basically the same idea as before, or that we've been using the whole time. Now, notice it says the function should be positive, continuous, decreasing. And notice it says from 1 to infinity. Now, it doesn't have to start at 1, right? So if, say, this sum here was n equal 3, well, then you would just start your integral at 3. So let's go ahead and try one of these. And notice it says your function that you plug into the integral is nothing more than the sequence inside the series. So basically, you're just turning the sum into an integral from 1 to infinity, 5 over 4 n to the 15th. Now, instead of n, we're going to switch to x. And as a technicality, right, I'm going to do this the first time, and then I'm not going to be too leery about it. We should make this limit c approaches infinity because that's technically an improper integral. So all I did was change the sum into an integral. Because it has an infinite bound, it's improper, and therefore I need the limit out in front. And I went from n to x. Now we did this one yesterday up here for the P series. So you should be able to look at that quickly and tell me, did that one converge or diverge?
Diverge.
Are you certain?
converge.
Are you certain?
Yes.
Okay, why?
Because 15 is greater than 1 in the p-series, and it converges. And then
1 over n to the 15th is 15. If p is greater than 1, we get converge, right?
yeah.
We already know that this series converges, so let's prove it now using the integral test. So 5/4, that could come out in front. Okay. Anna, do you mind muting your microphone again, please? Thank you. So 5/4 comes out in front. Limit, we still have the integral from 1 to c. And I'm going to rewrite that as x to the minus 15 dx. So the integral of x to the minus 15, we add 1 to the power, it becomes minus 14. And then you divide by that number, right? So I'll pull out the negative 1 over 14. Let me get that. Because this is this if we were to integrate. So what happens to 1 over c to the 14th as c approaches infinity?
It approaches 0.
Right, so this will go to 0, which means we just get a negative 1 times all this stuff out in front. So that's going to be what, 5 over 56? All right, so that number really doesn't have any significance other than the integral converged because it gave us something that we can work with, right? A real number. So if the integral converges, so does the series. And I keep saying things like by integral test because I want you guys to get used to not only saying does it converge or diverge, but to tell me and whoever else you might be doing this for, you know, what test you're using. All right. Guess we could do one more. I think I'll do C for you here. And I'll leave B for you guys. So again, I need to translate this into an integral. So 1 to infinity. And instead of n's, I want to do x's. And again, I should put limit as c approaches infinity and then make my upper bound c. Now in physics, and I assume in engineering, we tend to not write those limits as much. We just understand that we're going to take the limit. So we're going to be a little lackadaisical here. and leave that alone for now. So this is a by parts integral. I would let u equal x, du equal dx, dv e to the x dx. Therefore, v is e to the x. So we get x e to the x minus integral e to the x dx. And we've done this one quite a few times now. Of course, this has to be evaluated from 1 to infinity, and so must this guy. So all of that evaluated from 1 to infinity. I'm going to rewrite it as this. So that second part would technically go to 0, but in all reality, it doesn't really matter because this guy is an exponential times a linear function. The exponential will win because it increases or decreases more rapidly, and therefore it tells us what that function, this overall function, would do, and it tells us it heads towards infinity. So if that's the case, we get diverges, right? Again, by integral test. All right, so that's one example of each type. And of all the things we've done so far, this should probably be the most familiar because we finally get to use some of the calculus we've been learning along the way. So any questions about the integral test before I move on? All right. So I'm going to do one of these problems for you. And I may make the other one a quiz question for you guys to do, depending on how much time we have today for you to work on problems. So far we've done how many tests? We did tests for divergence, we've done p-series, integral test, geometric series, telescoping series. Have I missed any? That's all 5 that we've done so far. And at the very beginning, right, I told you that we want to know, does something converge or diverge? And the whole point of that was, if it diverges, it's useless, right? We can't use something that diverges. So here's a series, or they're telling us we have a series that is already convergent. And it says we want to estimate the sum to a specific error. So basically what's happening here is we're saying, okay, so first off, the whole reason we learn all of these sums is that we want to make substitutions later on down the road when we're solving problems. And the best example that I can think of off the top of my head and I hope I have this equation right, is this guy. Let me do theta instead. So you get something like this equation here, and this is actually an equation for motion for a pendulum. Right, so little guy swinging back and forth, right? There's our theta. So this is an equation you would see, say, in physics for the motion of a pendulum. And this is, in fact, a differential equation. I don't know how many of you are familiar with the dot notation, but this is theta double dot. And that means basically just the second derivative of theta. So we've got the second derivative plus sine of theta equals 0. That differential equation is what we would call nonlinear, and we did not learn how to solve these yet. And in fact, some of these can be quite difficult to solve. So eventually what we're going to do is, once we get through all these tests, we're going to learn Taylor and Maclaurin series. Those are going to allow us to generate polynomial representations for just about any function. So basically, we're going to get to a point where we're going to be able to prove that sine of theta can be approximated by theta, but only for very small angles. Okay, I said all of that, right? That's a lot of new stuff. The point being, we could then solve this equation with no problem, right? We could turn this into a separable differential equation now. So how does that relate to this error? Well, at some point in your career, right, you're not going to be doing this stuff by hand necessarily. You probably will be asking a computer program to do it. And then you're going to tell the computer, I need to know this thing to a certain error, right? You might need 2 decimal precision, or maybe you need 8 decimals, right? Depends if you're building a bridge or sending a rocket to Mars, right? Depending on what kind of precision you need. So this allows us to say, okay, I've got a sum, I'm trying to solve some problem, and I want to be this specific in terms of how accurate I want to be. So how many decimal places? So what was done here is you start with a convergent series. They take the series and they translate it into an integral, right, from 1 to infinity. And then they use a property of integration that says, as long as this thing is continuous, then I can split this integral somewhere in the middle between 1 and infinity, and they split it at some value n. So we can integrate from 1 to n, and then from n to infinity. So then they say, okay, the integral from 1 to n, well, that's going to be my approximation. And the integral from n to infinity is going to be the error. So let's look at this first example down here. It says, show that the series is convergent, because otherwise there's no point in continuing. Then find how many terms n are necessary to ensure that the sum of the series is accurate to the given value. And then finally, use Excel to prove that you get the right value for S. All right. So first we need to prove, is this series convergent? Well, to me, this looks like a P series where P equals 5. And if P is greater than 1, then it converges. So for part A, convergent by p-series. Part B. Find how many terms n are necessary to ensure the sum of the series is accurate to the given value. They ask us to be accurate to the 100,000th place. Okay, so tens, hundreds, thousands, 10,000s. Now it says 100,000s. Now the way we do this is when we get to the 100,000th place, we put a 0. We go one more and put a 5. So whatever the accuracy asks for, go one more place and put a 5. Why do we do that? Well, we all know that if the next digit is a 5, we round up. Okay. And okay, so how many terms n? Okay, so we want our error, right? That's this number. We need an integral from n to infinity of, instead of 1 over n to the 5th, we're going to make it x to the 5th dx. And it's important that you don't leave it as n, because one of your bounds is n, and it's not okay to integrate over something and have a bound that is the same variable. So then we just need an inequality in here. And at this current second, I don't remember which direction I want it. I think I want it this way. We'll find out. Right, if we want to be within that accuracy, then we want our error to be less than that number. All right, so let's take care of this integral. 1 over x to the 5th dx, that's really x to the minus 5 in there, right? To integrate that, we would get x to the minus 4 over minus 4, or minus 1 over 4x to the 4th, evaluated from n to infinity. So this is minus 1 over 4. And 1 over 4 n to the 4th. Hopefully it is clear that this goes to 0, right? I'm dividing by really big numbers. And so I'm left with my decimal over here, greater than or equal to 1 over 4n to the 4th. Now the whole point was to find n, right? It says, find how many terms n are necessary to ensure that the sum is accurate to the given value. So we're trying to find out how many terms do I have to take out of this sum so that I can get to that accuracy. So I'm going to multiply by 4 over there. Actually, I'm going to move this decimal down here. And I'm going to take n to the 4th and put him over here. So I'm going to have n to the 4th greater than or equal to 1 over 4 times this decimal. So 1 divided by 4 times that decimal is going to be 50,000. But that's okay because I have to take the fourth root of both sides. And that comes out as 14.95. Now I'm going to tell you that these are somewhat tricky in that it's always hard to tell if that means 14 terms or 15 terms, right? You'd expect to round up there. I'm just going to suggest anytime that you've gotten or you get a decimal, so any leftovers after the whole number, always round down. So I'm saying that this tells me we need 14 terms to get that accuracy. So I'm going to open up Excel. Because I want to show you what we just did. So I need first my values of n. Let me go ahead and zoom in a little bit here. So I'm just going to, we start at 1. So I'm going to do 1, 2, 3, 4, and so on. Then I want to do equals our term inside of the sum was 1 divided by n to the 5th power, right? Okay, so each one of these is the term that corresponds to n equal 1, 2, 3, 4, and 5, and so on. So this is a, let's see, can I get a subscript? I could just do it this way. Okay. And then this is going to be the sum. So this should equal the sum starting here. I think, let's see if I hit F4. No, I thought it was F4. Oh, hold on. Function. F4. There we go. Okay, the reason I did that is now that's going to take and start with that number each time. So the dollar signs tell Excel that I always want to start with that value. What are you doing here, computer? I don't want these to be the same. There we go. Let's see if that's enough to get it to do it properly. Nope. Okay, let me do another one. Still doesn't want to do it. I just need Nope. Not sure why it doesn't want to keep my running sum for me. Just give me a second here to calculate them. That looks right. That looks right. And for some reason, it just wants to start over. Okay. So I believe they should all be good now. Let me expand this cell. And then that should be fine. Okay. So we were trying to be accurate to 5 decimal places. Why is this one green? That's fine. So 1, 2, 3, 4, 5. Okay, so we're looking for the digits to be the same all the way out to 5 decimal places. Well, this is 368, 369. Looks like 369 the whole way. Okay. Then the next digit looks like 3692, and that stays the same. So that would be 1, 2, 3, 4, 5. Okay, so 3692 looks like that is the accuracy that we want. Now the question is, when is the first time that it does that? And then when does it start to repeat and continue from then on? So here's the first time that we have 03692. That only took 13 terms. But notice the first time that it repeats is 14 terms. So we solved that it would take 14 terms to be accurate to 5 decimal places. So what do we mean by accurate to just 5? Well, if it'll let me, I can stretch this out further. And I can do the same thing here. And if I will work here, let's hope. Okay, so that seemed to work fine. So let's go ahead and do some more. So notice all of these are 03692. The digit after might change, but they're all 3692. And I can do this for as many terms as I like, but it shouldn't change from those first 5 digits. So my sum that I'm looking for is that. So first, how many of you are still awake? Not awake? Okay. How many of that, or how much of that made sense to you? I don't know what thumbs up means for how much. 1%?
It all made sense to me.
All of it?
Yeah,
Don't lie to me.
I'm not lying. I use Excel a lot in school, so like, it's just like the math, like the figuring out the like terms. And so my one question is, do you, so the first time the accuracy repeats itself is where n, what n equals?
Yeah, so whatever n tells you, it's typically the point where it first repeats the digit you're looking for.
That makes sense. Okay.
So there's another one there. If we have time, I'll let you guys do it in class. If not, I might give it to you as an outside problem. So any other questions about estimation of a sum before we continue? Okay. So are you guys okay to move on to the next topic before I ask you to do your own problems? Or do you think it'll be too much at once?
We could do the questions first, and then that way we get the enforcement of understanding if we do know it or not, and then we can continue the lesson.
Anyone else want to weigh in? I think there's only really one problem for you to do. Just the integral test right now.
Yeah, I'd rather like do some more like of the next guided notes.
Sorry, Han, I agree with that sentiment.
It's all good.
All right, so this stuff, I think maybe a little more straightforward if that last section was kind of confusing to you. We have two comparison tests we want to look at. We want to look at the general comparison test, which I am not particularly a fan of. I think it's a little too arbitrary to use often. It is, I mean, it can be used pretty well, but I'll just show you when we do it why I'm not a huge fan of that one. The limit comparison test, I think, is a much stronger option. And then if we have time, we can look at the alternating series test. So comparison test, the whole point of either of the comparison tests is we're given a series and we look at it and we say, okay, I don't have a test that looks like would be a good choice here necessarily, but it does look very close to a series that I do know how to work with. So notice this first example here. It says the sum of 1 over n cubed plus 1 is very similar to the series 1 over n cubed. Now 1 over n cubed, that's a p series. And we know how to work with that quite easily, right? If p is greater than 1, it converges. So notice it says down here, when selecting a series to compare to, you're going to take the dominant terms in the numerator and the denominator. Dominant meaning it grows faster. So obviously, if we have an exponential versus a a linear function, we would take the exponential. And then the rules for the comparison test, the general comparison test, are as follows. if you choose a B, so first off, the sum A sub n is the one you're given. The sum of B sub n is the one that you come up with. So if B sub n converges, you must also show that the sum of A sub n must be less than or equal to the sum of B sub n. And then you can say A sub n converges as well. If you create B sub n and it diverges, you must also show that the sum of A sub n is greater than the sum of B sub n. And if both of those are true, then you may say A sub n diverges. So there's two criteria here. And the reason I'm not a huge fan of the comparison test is this sum less than or equal to situation is not the most easiest thing to figure out. So I'll give you a couple different ways to do that. Let's go ahead and try the first one, and you can see what I'm talking about. So first off, we need to take dominant terms of the numerator and the denominator, and that'll create our sum. So the dominant term here on the top obviously has to be 3. It's the only term. And there's two terms on the bottom, 2n cubed minus 17. So we're going to take the 2n cubed because minus 17 doesn't change. Okay. And if we want, we could take that 3 halves out in front. And now I've got a p series. P equals 3, which is greater than 1. Therefore, it converges. So we've proven that B sub n converges, which means we are trying to show this bullet point. So that tells us we are looking for the sum of A sub n to be less than or equal to the sum of B sub n. So how in the world do we figure that out? Any ideas? So one way you can do this is try to find the sum for the first, say, 10 terms. So first 10 terms here would be starting at 3. And that would go to what, 12? So 3, 4, 5, 6, 7, 11, 12. Yeah. And you can go more than 10. It doesn't really matter, but just a general rule of thumb is to at least try 10. So now the question is, okay, well, how do I do that? Right? Because we're not going to have Excel to do this each time. Well, we can do it on our calculator. So let's go ahead and try that. Let me go ahead and get some more light here. So we want to sum. Anybody remember where to find that on your calculator?
Math 0.
So it's under the math tab. So click math, the math key on the left-hand side. Then scroll down or hit 0. Well, it depends on the calculator that you have as well. So mine is 0 and it says summation. Okay, so I'm going to choose that. And then it pops up really nicely with a sigma and these little blocks that I have to fill in. So the first block is X or N or whatever variable, it doesn't matter. And we're going to start at 3 and we're going to run to 12. And our first series was 3 divided by 2n cubed minus 1, right? So I have that all typed in now. And I'm going to run that. And I get 0.112. Then I'm going to hit second enter. That's going to pull up the same thing that I just typed in. And I'm just going to get rid of that minus 1 down there. And then that's going to be my B sub n. And there I get 0.1107. So I got that A sub n. Oops, it was minus 17. Minus 1. Silly me. Okay. So fixing that, sorry about that. The sum A sub n I got was 0.1412 and B sub n was 0.1107. 408 if you round up. That is not less than or equal to. So I only got one of the two criteria, right? I got B sub n converged, and I got that the A sub n sum was greater than the B sub n sum. So what can I say? Do you remember what we said for test for divergence if it didn't work?
Use a different test.
So we would say inconclusive, right? And you would need to try a different test. All right, so I'll do one more of these for you, and I'll leave the last one for you. So this second one here, can you guys tell me what you would choose for B sub n? What are the dominant terms here?
Would it be sine squared n over 5 to the n?
So 5 to the n I do agree with. And well, first off, thanks for answering. So sine squared, looking at it, you would think that's got to be bigger, right? It's got n in it, it's going to change, so that just automatically makes you think got to be the greater term. But if I plotted sine squared, right? So originally sine looks like this. And then sine squared should do this. What is this value here? Everybody know?
Is it just 1?
Right, it's bounded by 1, right? So can sine squared be bigger than 2?
No.
It can only be as big as 1, right?
Yeah.
So in fact, 2 is actually the bigger term there. So that one's a tricky one. I don't think anyone's gotten that on the first try, so don't feel discouraged by any means. So those are our dominant terms. What kind of series is this?
P series.
Yep.
Or
Remember for a P series, it's got to be n to the power P, right?
right.
Here we've got a constant to a power n. So think back maybe a little further.
Geometric.
Not sure.
It's geometric, right? We can write it as 1/5 to the n, because 1 can always be 1 to the n. So for this, r is equal to 1/5. Absolute value of that is less than 1. Therefore, it converges, right? Remember, that one's backwards to the P series. If P is greater than 1, it converges. If R is less than 1, it converges. All right, so we've got B sub n being convergent, which means, again, we're looking at the first bullet point, which means we need to prove the sum of A sub n is less than or equal to the sum of B sub n. So again, you could plug in the numbers in your calculator. That's probably the most accurate way to do this. Let's at least just discuss the other two types. The other options you have are to plot them. And if one of them has terms that are greater than all of the other, then its sum must also be greater than the other one. The other option is to try and look at the equation and determine what the terms are going to look like. So in this case, that's kind of hard because sine squared is going to be moving between 0 and 1. So that the numerator could be anywhere between 3 and 2. And the denominator, right, 5 to the n plus n, that's obviously going to be bigger than just 5 to the n. So let's go ahead and just calculate the first couple terms. So this is going to be 1, 2, 9. Let's do the first 15, see what happens. That should be right. No. 15. Actually, that'd be 16. Oh, wow. All right, so let's go math 0. That brings up our little summation for us. I'm going to go 1, 2, I'm going to do 1 to 14. My first function is 2 plus sine of n quantity squared. Does this have a gigantic parenthesis all of a sudden? Okay. Divided by 5 to the n plus n. Yeah, something wrong with the input on here. It doesn't want to accept the sine squared very well. If that fixed it. No. Okay. Whew, that was weird. All right, now let me do it for just 5 to the n. And hopefully you guys are doing the same thing. So I'm moving along here, not just sitting and listening to me fumble with the calculator. So somebody tell me what they got for their numbers. For these, I got these two things. I'm not sure I like those numbers though. So like I said, the input was acting strangely here.
I got 0.577 and 0.499, but I don't know if that's right either.
That sounds more like what I remember.
Got that as well.
Yeah, I think one of my parentheses got misplaced, and then it started screwing with my summation. For some reason, it was putting in a really large parenthesis, and I don't know why. Can you read those again?
Yeah, so the sum of A sub n was 0.577, and sum of B sub n was 0.499.
So once again, it looks like we don't meet the criteria, right? Because A sub n is actually greater than the sum we got for B sub n. So once again, unfortunately, inconclusive. Now I'm pretty sure the one that you guys do is going to be conclusive. All right, we are okay with those first two? Questions, concerns, thoughts?
For the sum of Bn, I got exactly 0.5.
I mean, it's 0.499 something, so it's pretty close. Did you run from 1 to 14 or 1 to 15?
1 to 15.
That might be why.
Oh. So put it in the calculator as 1 to 14 for both AN and BN.
Yeah, try that.
Okay, thank you. Yeah, I got 0.499.
So you can see that, you know, if you did 1 to, I don't know, 30, right, it's not going to make a whole lot of difference. The numbers are going to start getting so small that they're not really going to add anything to it. Right, you went from 0.499 to 0.5. You might be at 0.501 or something. So that's why I say you can typically take the first 10 terms or so, or however many you choose, but at least 10. And if you're so like 3 to 12, I'm sure some of you are going, I have no clue. Why did you pick 12? So counting principles say that if you have two numbers and you want to know the amount of numbers between those two values, you take the first number, subtract the last number, and add 1. So if you literally count on your hand starting at 3 and go up to 12, right, you'd count 10 numbers. The reason you add the 1 is because you have to start with the first number. Right? If you just subtract the 2, you're eliminating starting at the first number. So if you ever want to do exactly 10 terms, just take the the number you come up with for the top minus the bottom one plus 1. That'll tell you how many terms you're taking. So I'm going to leave C in this category for you guys. The other thing, let me go ahead and, as I said, the graphical and kind of argumentative option for B is kind of difficult to see. I wanted to at least discuss it here for part A really quick. So what I was trying to say was, right, the second part of the criteria says the sum for A sub n has to be less than or equal to the sum of B sub n, for instance. So if you look at this and you look at what we came up with for this, right, the A sub n, the denominator is going to be smaller for every one of those terms because I'm subtracting 17 from it. And if my denominator is smaller, that means my overall number will be bigger. So every term in A sub n will be bigger than its counterpart in B sub n. Does that make sense to everybody? So that's kind of an argument you can make and say, okay, so if all of the A sub n terms are bigger than all the B sub n terms, then obviously the sum of A sub n for any amount of n is going to be larger than B sub n, which is what we found. So I just wanted you to keep that in mind as well if you wanted to kind of use that as a double check method for yourself, other than just plugging in the numbers. All right, so that was comparison test. Now we get to do limit comparison test. And this is, I think, much easier to comprehend. We are still trying to find a B sub n that we come up with. We're still doing that by finding the dominant terms. We are still proving that B sub n either converges or diverges. But instead of doing this sum or guesswork with how does the sum of A sub n compare to the sum of B sub n, we are now taking the limit of an over bn, and if that limit returns some number c that is real and greater than 0, so basically a positive real number, then whatever we got for B sub n also happens for A sub n. So it says both converge or diverge. So if we prove B sub n converges, we take the limit, we get a real positive number. A sub n also converges. So let's just jump right in and try one and see what happens. So first of all, we need to come up with the B sub n term. So take the dominant parts. Obviously, it's 2 on top. And on the bottom, it's going to be 4 to the n. That is a geometric series, right? If I put a summation in here, you can pull the 2 out in front, and that would be 1/4 to the n. Absolute value of r is absolute value of 1/4 in this case. That is less than 1, and therefore we get convergent by geometric series. Okay, so B sub n converges. The next step is to take the limit as n approaches infinity of A sub n, which is 2 over 4 to the n plus 2. And I would typically divide by B sub n, but because these are fractions, instead of dividing, I am going to multiply by its reciprocal. So 4 to the n over 2. Then I want to simplify this best I can and evaluate the limit. So these 2's here cancel. And it might be kind of difficult to see how to evaluate this limit. If we tried to just go ahead and plug in, we'd get infinity over infinity, and we might want to be tempted to use L'Hopital's rule. However, it's not often that we take derivatives of constants to a variable power. So the easiest way to do this one is just divide everything by 4 to the n. Now when I evaluate the limit, anything to the nth power is going to become infinite, and 2 over infinity is going to become 0. So I'm going to get 1 over 1 or just 1. That is a real number that is greater than 0. Therefore, a sub n does the same thing that b sub n did. We found b sub n was convergent. Therefore, a sub n converges. And we'll say by limit comparison test. Everyone okay with that? I'm trying to think which one, what other one I should do for you. I think I'll go ahead and do C. So again, I need to start with the dominant terms to generate my b sub n. 1 obviously on top, it's the only thing there. Dominant term on the bottom. So is n bigger or is n minus 1 under the radical? So let's think of a number like, I don't know, 5. Is square root of 5 bigger or is the square root of 4 bigger? Should be square root of 5, right? So it looks like root n is the dominant term. We could rewrite that as this. You should recognize that as a p series. P equals 1/2, which is less than 1, which means diverge. So b sub n is divergent. So the best we could do is prove that a sub n diverges. So we need the limit as n approaches infinity. I need a sub n divided by b sub n, or in this case, multiplied by the reciprocal. I'm going to go ahead and divide every single term by square root of n. All right, so square root of n on top becomes 1, square root of n on the bottom becomes 1, and then I just combined the 2 square roots for that term. So if you really want, you could do it like that, right? And then I'm going to rewrite that radical. So this is n over n minus 1 over n, or 1 minus 1 over n. And remember, limits are one of those really weird things that can go inside of radicals. So it can go in, and we could evaluate 1 over n as n approaches infinity. That piece is going to head towards 0. I'm going to have 1 over 1 plus root 1, or 1/2. That is a constant that is both real and greater than 0. Therefore, a sub n does whatever b sub n did. So it also diverges. Now, for instance, if, say, for some reason this limit came out to be minus 1/2, well, then the best I could do is say inconclusive. Because just like before, I have to have both criteria to be able to do something. So I have left B in this section, C in the limit comparison, and B for integral test. And if we have time, you can work on B for the estimation of the sum. So I'm going to go ahead and break you guys up, if that's all right with you, and give you guys a chance to solve some of these problems and ask questions and do whatever you need. Are you guys ready for that? Okay, I got one thumbs up. Anybody else? Yeah, okay. All right, so I'm going to go ahead and pause recording. So, Zoom recording, and I'm going to share the packet with you again. So I just wanted to look at alternating series tests. I think we have enough time to go ahead and do that. If not, then at least we were introduced to it today. So alternating series, I always found them kind of interesting because you find the piece that makes them alternating, and then in order to solve the problem, you ignore it, which I always thought was kind of funny. So in order for something to be alternating, it means that the terms that come out of the sum are opposite in sign. So you get a plus, then a minus, a plus, then a minus, as you see in the first example there. Or it could start out as a negative term, then a positive term, and vice versa. The terms that generate the alternating series, which are highlighted here, says alternating factors. These are just a few of those. So -1 to the n, -1 to the n plus 1, so on. We could also have trig functions like cosine n pi. Right, so you know cosine of pi is -1. If n was 0, for instance, cosine of 0 is +1. So that alternates back and forth. What about the sine one here? So if n is 1, what do we get? Actually, let's start with n equals 0. If n is 0, 2 times 0 is 0 plus 1, so we get pi over 2 inside there. Sine of pi over 2 is 1. If we let n equal 1, then we get 3 pi over 2 inside, and we know that that gives us back -1. So if you're curious, notice that 2n plus 1, that's actually how we represent an odd number. So 2n is even, 2n plus 1 is odd. So what is the test? Well, once we've identified a series as alternating, then there's two parts to the test. The first part says, prove that the series is decreasing. And it's written here as the absolute value of the sequence of a sub n plus 1 must be less than or equal to the absolute value of a sub n. All that really means is that the next term in the series or sequence must be smaller than the prior or the previous term. So if we were to say use this one up here as an example, we would get rid of the alternating portion. So instead of this being minus 1/6 and minus 1/12, we would consider these all being plus now. And the question is, does the second term look smaller than the first term? Well, yeah, of course, 1/6 is smaller than 1/3. Is the next term smaller than the one before it? Is 1/9 smaller than 1/6? Again, obviously, yes, it is. So this is a decreasing series. And part B says, now take the limit as n approaches infinity of that sequence, like the absolute value of a sub n. And if you get 0, then we're going to go ahead and say that that series is convergent. If either condition fails, we say it's divergent. Hannah says that your guys' paper says n pi over 2 for sine. So I must not have put up the most up-to-date one here. So yes, it should be 2n plus 1, because that term is not properly alternating. So we've got the two conditions. The first one, you can simply plot the function. And if it's decreasing, well, then we can say, okay, then so is the series. And then we need to take the limit. And as I said, the funny thing about this is these absolute values, all they do is get rid of these alternating factors. So let me do an example here. Cosine n pi over n. First part says, well, first we need what's the absolute value of a sub n? Well, that's absolute value of cosine n pi over n. The alternating part is cosine n pi, and the absolute value gets rid of that. So the absolute value disappears, so does cosine n pi. We don't have to worry about the n because n clearly runs from 1 to positive infinity, which means there's no way for that to be a negative number. And so I don't need the absolute value around it still. So plot that function. So I go to my trusty calculator and I say, give me 1 over n. And I only care about the first quadrant, obviously, because n is 1 to infinity. And I get something that looks like this. That function is decreasing, which means if I plotted the individual points, well, then they would just look like this. And they would also be decreasing. So to satisfy the first criteria, you just need to plot it and show that it's decreasing. To satisfy the second criteria, you need to take the limit as n approaches infinity of the absolute value of a sub n. Well, that's the limit as n approaches infinity of 1 over n. That's pretty simple. That goes to 0. So if we look back up here, it says we need to prove it's decreasing and the limit's 0. And if we do both of those, it's convergent. So by alternating series test, this guy converges. Let's see. Yeah, I think your term for this one is going to be incorrect as well. So you need to fix that on your packet. I don't know if any of these are special compared to others. Yeah, different. So first off, what is the absolute value of a sub n? Well, this just means identify the alternating portion and drop it. The alternating portion here is -1 to the n. So it will disappear and I will be left with these terms. So I want to plot that function. Now, if I do that, again, only looking in the first quadrant, this function does this behavior. So if we scroll back up, it says that it should be decreasing. Now, it does not specifically say for all n. And the reason for that is because it's okay for it to increase for a short period of time as long as the majority of the function is decreasing. So we can still say this is a decreasing function. So that meets the first criteria. The second one, again, says limit and approaches infinity of a sub n, the absolute value of a sub n, must be 0. Or at least we're hoping it to be 0. So you plug in infinity here, you get this guy. That should indicate to you that you need to use L'Hopital's rule. And I think we've even done this problem already. So I took derivative of top and bottom, plug in again. I get the same thing. So I use L'Hopital's rule once more. Now I get 2 over infinity, which is 0. So that is both of the criteria. Therefore, converge by alternating series test. So I don't think that this is too terrible, right? You just have to identify the alternating portion. basically get rid of it and prove that the function decreases and the limit goes to 0. And if either of those two things are not true, then you just say diverges. So we've got about 9 minutes left. I'm going to go ahead and break you guys up again and give you a chance to try those last two.